Welcome everybody to our presentation. We're the super seniors out of the University of Texas at Austin, and our project is over Luminous navigation markers for lunar surface EVAs. So what we'll be going over today, we'll start with an introduction to the team, go over the project background, the concept of operations, as well as the design concept, risk and safety factors, as well as some challenges we ran into, and we'll end with the project budget and timeline. So for our team, I'm Lauren, and I will be going into the Air Force OTS after graduation.
My name is Robert. I'll be graduating in December and commissioning in the Navy.
My name is Briggs, and I'm currently a pilot select in the Air Force.
Hey guys, my name is Jorge, and I'm currently a flight attendant for Republic Airlines based in Miami, and I've co-opted at Delta Airlines Engineering.
All right, so our main problem that we're trying to solve is for navigation on the moon when you can't just use line of sight navigation, and there's no GPS system currently in place for the lunar surface. So there is a need for these navigational beacons that will allow for wayfinding on the moon. Our concept of operations is to have small beacons that astronauts can carry with them and drop along the way as they go for the first time to whatever their target destination is, and then these beacons will stay in place for future EVAs.
The beacon will be a pyramid shape with 4 telescoping legs and an LED at the very top point of the pyramid, attached to a smart microcontroller and radio transceiver that will allow it to behave as a proximity sensor. The microcontroller conserves battery power by allowing a low-powered LED to blink at a set interval depending on the distance between the beacon and the astronaut, and to completely turn off once the astronaut is out of range of sight. The beacon will be deployed by the astronaut pulling out the telescoping legs using a tool and pressing a quick release button that will release the solar panel petals and allow them to hang at a 90-degree angle with the moon surface, which will be an ideal angle to collect sunlight on the moon's south pole.
The 3 main risk factors that we had to focus on were 3, 9, and 5. So for number 3, that was making sure that the lunar soil didn't damage any of the components inside the beacon, and we solved that through using telescopic legs in the design, and we show that later in a field test. Number 9 was ensuring optimal angle for the solar panels to receive sunlight, and that was also solved through the design and is shown later in the assembly video. And lastly, our main issue, number 5, was our power issue. And George was able to solve that through the electronics design, and he's going to touch on it more now.
One of our biggest challenges is power management. It's also one of the mission requirements to be able to operate on just the battery for 2 weeks or 336 hours due to the solar night. The table above details the total power required to operate the beacon. At our current power budget and battery selected, the time until depletion varies from 27 hours with the LEDs turned on continuously to over 2,000 hours when placed in sleep mode, as can be seen in the table below. Our power management strategy would be to only turn on the LEDs of the beacons that are in range of our astronauts. This will be accomplished by employing a sleep timer and an interrupt sleep mode. For example, when the beacons are in range, they would be on an 8-second sleep timer, which means that only 20% of every hour would be devoted to drawing the 55 milliamps at full power, giving our astronauts over 10 hours a day to work near these beacons. When they are out of range, the interrupt sleep mode will maintain the current draw at a low 580 microamps. Let's see a demo of this in action.
The breadboard on the right is our beacon, and it's currently in interrupt sleep mode where it's consuming 585 microamps. To the left is our transmitter, and it's currently disconnected. Once our transmitter is in range, or it's powered on, then the sleep will be interrupted and the LED will blink for a couple of seconds. After which it will go to sleep on the watchdog timer for 8 seconds, wake up, and listen for a new signal. If no signal is found, it will go into the interrupt sleep mode, where it will stay until it finds a new signal. So let's see what happens when a transmitter comes in range. Let's change the setting to milliamps. So here you see it woke up where it's consuming 12 milliamps until a signal is found. Then it goes up to 59 milliamps at full power when the LED is turned on. Here we see it go into the 8-second watchdog timer sleep mode, where we get the best power savings at a rate of 390 microamps. Then the cycle begins again. It wakes up, listens, there's a signal, so it powers up the LED and it goes back to sleep. Now if I disconnect it, it will go back to its 8-second nap, And when it wakes up and there's no signal available, it will slip into the interrupt sleep mode where it consumes 580 microamps. But it's really quick to be interrupted, so as soon as the signal is in range, then it goes right back to the lighting condition. In order to meet this challenge, we resorted to destroying the onboard LED, thereby saving 2 milliamps and an order of magnitude. The astronauts would have the same microcontroller and lower radio transmitter embedded in their spacesuits, or they could have a very small puck-like device that houses a microcontroller, transceiver, and a small battery attached to the outside of their spacesuits with a small carabiner or similar attachment device. Once a device has been deployed, the beacon will use a lower radio to communicate with the puck attached to the astronauts. The distance between the puck and the respective beacon will determine the lighting configuration at the top of the pyramid. We'll use the RSSI, or Received Signal Strength Indicator, on the receiver to determine if the astronauts are in range of the beacon. This RSSI is a negative number measured in decibel milliwatts that ranges from negative 45 to about negative 135 on our lower modules, and it gives us a rough estimate of our distance. Basically, the closer we are to zero, the closer we are to the device. The further from zero, the further away from the device. Let's see how this works. So here we're receiving the signal and storing it in our incoming stream, but now we're parsing the data for the RSSI and SNR values and storing them as integers in order to perform comparison operations on them to change the lighting configuration of our beacon. So I've set up this threshold of negative 50 in order to demonstrate the proximity sensor at a small scale. And if the signal strength is less than or equal to the threshold, then we'll light up our green LED 3 different times, so it'll blink 3 times green. But if the signal strength is greater than our threshold, then it'll cycle the red LED once. We've also set up an LCD on our test rig in order to monitor the signal strength and perform some range tests out in the field. So when they're close to each other and the RSSI value is greater than our threshold of negative 50, then it'll blink red. But if I move it away, it'll start blinking green as our signal strength drops below our threshold of negative 50. And when I bring it back, it'll go back to blinking red.
So for our prototype design, we made CAD models that were made as separate pieces and were designed to be assembled post-print instead of printing the entire beacon as a whole. The main challenge for the 3D models was designing the hinge deployment mechanism, and we decided to utilize a pin release lock system. However, we were unable to run through enough iterations of the design to get the deployment mechanism working at 100%, and you'll see this in the next video.
So this is a quick time lapse of the assembly of the internal casing for the beacon. This second time lapse is for the outer petals and some modifications I had to make to the beacon. This is the beacon fully opened up. And this next part is the beacon in a fully deployed state to collect sunlight on the moon. Here's a rough example, the first iteration of the pin release function.
To test the beacon, we did a drop test in sand, and we also tested the range of the lower radios and the visibility of the LEDs as seen in the following videos. Here's a video of the drop test we conducted. We dropped it from about 2 inches to simulate about a foot on the moon, which is what we calculated the astronauts would drop it from. As you can see, it does not sink into the sand very much at all, and it holds up pretty well.
We performed a range test and were able to get about 1/3 of a mile in the suburbs of Houston without line of sight. We also performed a visibility test, and despite it faintly showing up on video, it appeared clearly to the naked eye, even in the light-polluted city of Houston.
This budget report shows the price per beacon. We built 5 working prototypes for our field test, and we also encountered some challenges in sourcing some of the parts, so we had to make changes from the original microcontroller, LoRa radio module, and some alternate LEDs that we had designed for. Ultimately, we were able to maintain the essence and intent of the original design in spite of the challenges. That concludes our briefing. Are there any questions?